Okay, well, thank you, Arena, for the very kind introduction and for the invitation. It's a great pleasure to be here. As we were discussing a few minutes ago, I've actually never been to NC State. However, I grew up a huge basketball fan, and NC State was one of the programs that I always had my eye on. So I've known about the university for a long time, and like I said, it's quite an honor. And as also mentioned by Irina, I'll talk about a conjecture of Meissner. This isn't actually a problem that I've worked on, but I've known about it for some time now. And just over the holidays, just being just looking for something interesting to think about mathematically, I came across it again and thought about it for some time and decided that there's some things I should try on it. What the hey? And so today, I don't have a bunch of results to share with you. My hope is to just give you my take on this problem, and time permitting, maybe ask a few questions that I hope might lead to some new understanding. All right, so I'll start out. So the problem is really a three-dimensional problem, but I'll start out in 2 dimensions. And just as simple as it can be, we have the notion of convexity, and so a convex set between any 2 points, we have the straight line segment that remains completely within the set. And just for a little bit of just for the convention that I use is in the plane, I'll typically just work with the boundary curve. And so I'll call that a convex curve, just the boundary of a bounded convex figure. Another important notion for us will be that of the, let's see, here we are, that of the width in a direction theta. So you give me a theta point on S1 or an angle made with the x-axis as drawn right here in the lower left. And what I do is I find 2 supporting lines that are orthogonal to this direction made by theta, and then I look at the distance between those lines. Okay, that gives me a number, a non-negative number. I call that the width in direction theta. So if the shape is really flat in that direction, then W is going to be small, and if it's long as shown here, it's going to be a bit larger. All right, and so the objects that we'll focus on today will be curves and then later bodies in space of constant width. And so in the plane, a curve of constant width is 1 with W theta equals 1 for all theta. Okay, so this blue curve on the slide is a curve of constant width, one that I cooked up on my computer. And these 6 lines or 3 pairs of lines are all parallel supporting lines of a fixed distance that are all, so here I'm thinking distance 1 apart. You can obviously have constant width 2 or 3 or any other number, but I think 1 will be good enough for what we're doing today. So at that scale, these lines, these pairs of parallel lines are all distance 1 away. Okay, so hopefully that notion's okay with you guys. If not, like I said, just ask. And if I happen to miss the question, Arena, please just interrupt me. The simplest example, the simplest concrete example is just a circle of radius a half. Any 2 parallel supporting lines are going to be distance 1/2 from the center. And so if I add a half to itself, I get 1. So there we have the circle. Another example that will come up again and again today can be constructed as follows. So if I take an equilateral triangle, each of the sides of length 1, I can look at the intersection of circles of radius 1 centered at each of these vertices. So there are 3 circles. And then I can look at this shape that's traced out on the inside here. So if there are 3 disks, then it would be the intersection of those 3 disks. But if there's 3 circles, then I'll just consider this curve that I'm tracing right here, and I'll draw it a little bigger for you. It's known as the Rouleaux Triangle. It's 3-sided, 3 circular arcs. It has 3 vertices, the same vertices as the equilateral triangle. Not too hard to see that if I take any 2 supporting lines, any 2 parallel supporting lines, then at least one of them will be supporting the curve at a vertex. So in this picture, it's this one. And the other one will be supporting the curve on a circular arc, which is a piece of a circle centered at that vertex. And so the distance from this line to this line is the radius of that circle. In this case, it's just 1. So the Rouleaux triangle is indeed a curve of constant width. And we can cook up many more, just like this one. So here's a 5-sided. So these are called polygons, Rouleaux polygons. So curves of constant width consisting of circular arcs. And so here's a 5-sided regular pentagon, regular because each of these circular arcs have the same length. Not too hard to argue, just as we did for the Rouleaux triangle, that this one has width 1. Given any odd number, we can find a regular Rouleaux polygon, 7, 9, 11, 13, on and on. They do exist. And irregular polygons also exist of constant width for any number of sides larger than 3. If you're a 3-sided polygon, then there's only one, the Rouleaux triangle. But otherwise, there are more. I didn't draw one for you here. It's a little bit easier to draw the regular ones on a computer just because there's just less parameters to deal with. And as you may have just guessed, or if you're just thinking about what I said about the, for any odd number, I can find a regular Rouleaux polygon, then it's clear there are infinitely many examples. So there's a whole class of figures that are out there that are curves of constant width. And so here are 6 distinct ones that I just drew on my computer. I drew with Mathematica. And so the problem that I want to discuss with you today is figuring out which ones enclose the most and least area. Okay, and in addressing that problem and in just generating examples to learn from, a tool that we'll use is the support function of a convex set in general, or just in the plane here, we support function of a convex curve. So if the origin is on the interior of the curve, then what I can do is, for any given direction determined by theta, I could look at the distance from the origin to the supporting line whose outward normal is given by theta, or the unit vector that makes an angle theta with the x-axis. Okay, so that's this distance right here, h of theta. And another little fact I'll use. So there's some constraints which we'll discuss here in a moment on support functions. So you can't just give any function and it'll be the support function of a convex curve, but it's not hard to figure out what the conditions are. But I'll use that given an appropriate function h of theta, which satisfies a couple of basic conditions, then I can associate a convex curve to it. So sometimes I'll sketch a proof just in terms of the support functions and just quote that fact. So I'm going to be a little sketchy about that and not be so precise, but if there are questions, feel free just to ask about it. Okay, so the first question is, how do I plot the curve? I mean, say I'm given h and I tell you it's a support function of a convex curve. Well, it's not too bad, because what I can, if x and y are coordinates of this curve, then when I look at the vector, if you will, from the origin to the point xy, well, its projection in this direction determined by theta is simply h of theta, right? So I probably could have drawn these a little bit wider, but if I think of this being the vector and then its projection onto this direction normal to the supporting line, then that's just length theta. Okay, and so we have this equation, this relation right here at the top of the screen. I should say there's a general formula for the support function. I'm not going into it because it won't really help us today, but I can write down, excuse me, given a convex set or a convex curve, I can just write down a formula for h of theta, but I'm just resisting that urge right here and just arguing a bit more geometrically. But okay, given h of theta, then I can find x and y from this relation simply by differentiating. If I differentiate this with respect to theta, I'll pick up two terms, one from differentiating this x and y. I assume now x and y depend on theta, their parameterization. And then another term from x, y dotted with cosine, the derivative of cosine and sine. But the derivative of x and y should be tangent to the curve. And this cosine theta, sine theta is normal to the curve. And so that term actually drops out. And using that little trick is possible then. So you get an equation, two equations and two unknowns for x and y, and you can just solve them pretty easily and write down a parameterization. So you can just take this now and just, go to your computer and plot curves. This is precisely what I did to generate those figures. If you want to do things like Rouleaux polygons, they're a little bit trickier this way. It's usually easier to do them another way. But in any case, here's one way, and I also want to tell you about the constraints about being constant width in terms of the support function. And the first, is simply the constant width condition, which is summarized in this equation. So h of theta plus pi is equal to 1 for all theta. And that's easily seen from the diagram because, well, I told you what h of theta was. But if I rotate theta by pi and look at the distance to the corresponding supporting line, well, that distance is just h of theta plus pi. And then, as I said to you, this distance, the distance between two parallel supporting lines, has to be 1 everywhere. And so we just, it's an easy derivation of this constraint. The next constraint is this second derivative constraint. Okay, so h double prime plus h is bigger or equal to 0. For the curve that we have in mind for any of these curves, this quantity actually represents the radius of curvature. So 1 over this quantity, whenever it's positive, is the curvature, and we want that to be positive. However, we do want to allow this to be 0 because this is what occurs at, say, corner points, like for the Rouleaux triangle or various Rouleaux polygons. So an example, one of the examples I plotted on my computer, I don't even remember what the h was. It's probably in a mathematical file somewhere. But if, so here's a function h which satisfies a constraint, and it's plotted here in blue. Note, it's pretty tightly coiled around a half. It doesn't vary too much around 1/2. If I integrate this equation over 0 to 2 pi, I'll see immediately that h has got to have average 1/2. And so these functions tend to be, just oscillating around 1/2. And this orange curve is this second derivative curve. And so it's positive in this case, or I shouldn't say second derivative curves, but it's the radius of curvature. And so it corresponds to this particular shape of constant width. And so it's a little something to keep in mind. I will say this for some shapes, the second derivative of h, the corresponding second derivative, may not exist everywhere, but even for Rouleaux polygons. But it will, this inequality will hold typically for all but finitely many theta. So I I won't make the distinction. Okay, so these are two constraints. Any function, any 2π periodic function that satisfies this one on the left and say this one for all but finally many points corresponds to a curve of constant width, and just something that we will keep in mind. Okay, so that's a little course on the support function. Now, another important notion will be that of Minkowski addition. So given two convex sets in the plane, I could add them up pairwise, which is what's here in this box, and I'll obtain a convex set. This is just a little schematic. If I take K1 and K2, just generic convex sets, and I add them up pairwise, and I'll get another one. Okay, and the reason why we're interested in this this notion is because, well, for two reasons. Very generally, it applies to the so-called Brun-Minkowski inequality. So if I let A of K denote the area of K, then the Brun-Minkowski inequality says that the square root of the area as a function of K is superadditive. It's a homogeneous function, so it's also equivalent to being concave. So the square root of the area is a concave function of convex sets. This also holds in vastly more generality. I'm thinking of convex sets right here, but you can plug in any sets, any measurable sets. It still works, and in any Euclidean, any dimension, in Euclidean space in general. We'll come back to it when we study volume, but for now, we're just looking at areas. When K1 and K2 are convex and equality holds, that can only occur if K1 is a dilation and translate of K2. This inequality also implies things like the isoperimetric inequality from geometry and a number of other things. It's very, very useful to know. Related to bodies of a given width, we have this lemma, okay, this characterization of bodies of a given width. Okay, and I want to prove that to you here in a line. I don't want to spend too much time on it, just give you a one-line proof. The crucial thing is that the support function behaves really nicely, plays well with Minkowski addition. So if I look at the Minkowski addition of two convex sets, K1 and K2, then the corresponding support functions, the corresponding support function is just the sum of the support functions of K1 and K2. So I won't prove that to you. If I had written down that formula that I said exists for how to express the support function of a convex set in general, then it follows quite easily from that, but we'll just take it as given. And okay, back to our lemma. So a set K is constant width if and only if when I add its negative to the set, I get the unit disk. So D is my notation for the unit disk. So now I'm thinking of sets, not just convex curves. And minus K, so by definition, it's the set of minus X, where X is in K. Geometrically, it's just a rotation by 180 degrees of all the points in K. So that's what that minus is. So it is a, I'm doing the Minkowski addition. No, K plus minus K is not 0. You do get a convex set, and the assertion again is that if it's, it's equal to the unit disk if and only if the shape had constant width. And so a one-line proof of that, well, if I take H of K and I add it to H of minus K, well, as I mentioned to you, H of minus K can be realized as the rotation of H of K through 180 degrees. And so that means H of minus K just turns into H of K theta plus pi, because this is what it means to rotate by pi. And that equals 1, as we noted earlier, if the set has constant width. And conversely, if I have H of K plus H of minus K of theta equal to 1, well, 1 is the support function of the unit disk, because if I go from the origin to any point on the circle on the edge of the unit disk, looking at a supporting line, well, that's just going to be distance 1. And so this is perhaps a too quick of a proof, but it really contains all the intuition we need to, well, at least to believe this assertion might be true. Okay, so I want to use this now to fashion a quite simple proof that the disk of radius 1/2 has most area among all constant width shapes. Okay, that's the first theorem, and this is an easy one. Okay, finding minimizers we'll see is tricky, but this is easy one. This is an easier one, and well, I'll comment on why in a moment. So if I look at, so the area of the disk of radius sorry, this should be a half, excuse me, I'm getting too excited here. So the disk of radius 1/2 has area pi/4. I don't know why I put that quarter in there. And if I take the square root of that, I'm going to get the square root of pi/4, which is the square root of pi/2. But that's the same thing as 1/2 times the square root of the area of the disk of radius 1, right? It's just the square root of pi. So if I multiply this by 2, I get this line right here. Okay, and now what I'll use is that lemma, which says that k is constant width if and only if when I add its rotation through 180 degrees to k, I get the unit disk. And now I'll use Minkowski, which gives me this lower bound. Okay, so here I've got the lower bound, the square root of area of k and the square root of minus k. And area is invariant under orthogonal transformations, and so this is just twice the area of k. And so then I have that the area of k is less than the area of the corresponding disk of width 1. Okay, so I say that's easy. I mean, okay, this is just a little few line proof, but it shouldn't be much of a surprise. You know, the area function is concave, and we're just finding a maximizer. Okay, it is quite a bit more tricky to find a minimizer. I mean, it's not even obvious that there is a minimizer, area minimizing shape among all curves of width 1. But it turns out that there is one, and this is the shape. It's actually even unique. It's uniquely minimizing. So the Rouleaux Triangle, one of our examples we discussed below, has least area among all curves of constant width. And this theorem is due to Lebesgue, from Lebesgue measure, and due to Blaschke, who was a prominent convex geometer. Well, I know him through his convex geometry, perhaps has done many other things. This theorem was proved independently by these two, I believe, in the first decade of the 20th century. So over 110 years or so, it's been known. So I want to give you, so there are many known proofs of this theorem. I want to sketch out one way to prove this, because I have my eye on the corresponding problem in higher dimensions. So there are shorter proofs than the sketch I'm going to give you, but the sketch will translate to some later questions that I'll ask. Okay, so here we are. All right, the first thing that we might want to know is, what are the extreme points? Okay, this is relevant because so I just argued for you that the area, or the square root of the area, is concave, and strictly concave in a sense. Okay, and so it makes sense for us to identify which sets are extreme. So it's almost like, I mean, if you think about it, if I give you a concave function, just say on a convex domain in the plane. Say I give you a concave function on the unit disk. Well, it may have an interior max, but if I minimize it, the minimum has to occur on the boundary. And for more general space, the right notion is, instead of boundaries, are extreme points. Okay, and so I call this set extreme if it can't be written as a non-trivial linear combination of two other sets of constant width. And I should mention, the linear combination in terms of Minkowski, the Minkowski sum of constant width sets is also constant. So I'm staying totally within the collection of constant width sets when I do this linear combination. And so it's what I mentioned again, but probably I should drive it home, is that if you give me a linear combination, a convex combination, excuse me, of constant width sets, well, by Bruminkowski, I have this lower bound. And if K1 is not a translate, so when I stated the equality condition for Bruminkowski, I said up to a dilation factor, but if I dilate a set of constant width, the only way it will remain a set of constant width is if that dilation is of size 1. And so, so I have strict inequality here if K1 is not a translate of K2, and they're both constant width sets. And obviously, this convex combination is bigger or equal to the min. And so if I want to minimize the area, I've got to look for extreme, sets that are extreme. Okay, otherwise just from this calculation, I see it, I won't get a minimizer. Okay, so that begs the question, what are the extreme points in the collection of bodies or figures in the plane of constant width? And we can answer that. Calais turns out answered this way back in the 70s. And so how does the argument go? Well, I mentioned to you before that any convex set, in fact, forget even just constant width, I have to have this lower bound on the radius. I mean, the radius of curvature is going to be non-negative. It's hard to imagine it being negative. For these support functions, I always have this lower bound that is bigger or equal to 0. And then I had this constant width condition, h of theta plus h of theta plus phi is 1. I could differentiate that twice, and I get this, just pretty easily. And then I add this resulting equation back to the original, back to the original one. And so I get this equation now, 1 equals 4 terms. And these 2 terms I can just throw away, in the sense of I could bound them from below by 0, because that just goes back into our condition, this lower bound, which we already had. So this claim is really just proving the upper bound. But once I throw these guys away, then I have that h double prime of theta plus h is less than or equal to 1. Okay, and so this gives me a bound on the radius of curvature, an upper bound that it's always 1. It also fashions a proof that the curvature, whenever, at any point in which it's defined for a shape of constant width, is at least 1. So it's just a constraint, nothing you can do about it. All right, so Calais Theorem, he wrote a beautiful paper. Doesn't really get, doesn't get a lot of citation, or hasn't gotten a lot of citation, but it's a beautiful little paper which proves definitively that K is extreme, K, a set of constant width, is extreme, if and only if its radius of curvature belongs to 0, 1 for almost every theta. And that's if and only if. Okay, so basically the radius of curvature has to take on one of these extreme values, essentially for every theta. Okay, so what's a good example? Well, the Rouleaux polygons. That's the prime example. Because if I look at any point on this shape, so here's our pentagon again, well, either I'm going to be at a vertex, and at a vertex, the radius of curvature is 0, so h double prime plus h is 0, or I'm going to be at a part of a, I'm going to be on a segment of a circle of radius 1, and by definition, radius of curvature there is 1. So at every point, at every theta, h double prime is either 0 or 1. So Rouleaux polygons are all extreme. Okay, now here's another thing that's a little bit, well, maybe just to me a little surprising. And that is Rouleaux polygons are dense. So if you give any set K of constant width and your favorite small number epsilon, then there's a Rouleaux polygon such that the corresponding support functions, the sup norm of which are within epsilon. This distance here actually induces a distance known as the Hausdorff distance between convex sets. If you don't know about that, don't worry about it. But the support functions have to be close. And moreover, the area function is continuous with respect to this distance, if you will. And so this Rouleaux polygon can be chosen to bound your area from below within epsilon, And so just naively, so I just took one of these shapes that, like I said, I just cooked up some shapes on my computer. This is back from the slide when I showed 6 shapes of constant width. And, you know, just looking at it, I thought, well, it looks like it has about 7 sides. So I just plotted here a regular, I guess it'd be a Rouleaux septagon, and superimpose these two, and it's not a bad approximation. So being a little bit more careful, you can get this difference to be as small as you like. Okay, and so there are 2 takeaways right now, right here from this slide. One is that I just argued for you that Rouleaux polygons are extreme, and so heuristically they're kind of on the boundary of the collection, the convex collection of bodies of, or excuse me, planar figures of a given width, but they're also dense. And so it's yeah, I just found that a little, or find that a little curious. So that's one takeaway, just one kind of curious observation. Probably just has to do with the infinite dimensionality of the problem. The other takeaway is that now I've reduced my problem to showing that the Rouleaux triangle has the smallest area amongst all Rouleaux polygons. Because if I can do that, then I could bound this area from below by the area of the Rouleaux triangle, and then I can conclude that the area of K, my fixed yet arbitrary set of constant width in the plane, is bounded from below by the area of the Rouleaux triangle minus epsilon, and epsilon's anything. So so this would fashion a proof of Lebesgue-Blaschke. Okay, so I'm not going to prove this theorem to you. I'm going to give you guys all a reference towards the end of this talk where these things are spelled out a little bit more geometrically than I like, not as much analytically. Although I should say Calais' paper proves this and much more, in fact. Proves even that there's a stronger distance for which you can use between these guys. So he actually adds the derivatives of the support functions and even estimates the number of sides of the Rouleaux polygon. So you can go much further. So I just want to talk about, you know, the area of the Rouleaux polygon. So a calculation I did on one of the boring days over the break is, well, if you give me an n-sided Rouleaux polygon, can you write down the area? And yes, you can. So you can write them down in terms of these interior angles. Okay, so here's the pentagon again, and just for schematic purposes. And so these interior angles that specify these circular arcs, so I call those xk's. Those, it turns out those sum to pi. That's actually another theorem which I didn't say due to Barbier many years ago, that turns out every curve of constant width has arc length pi. And so so when I look at these interior angles, they sum to pi because of that fact. N is an odd number, and it's also known that these interior angles here can be more than pi over 3. In fact, if any one is equal to pi over 3, then the shape is necessarily the Rouleaux triangle, just a little factoid that's known in the literature. So you can write down the area and show that it is minimized for the regular, maximized for the corresponding regular Rouleaux polygon. And it's minimized, well, it's at least equal to the area of the Rouleaux triangle, which I forget. Well, actually, I'll write it down for you in a moment. And so the little calculus problem, well, it's a calculus problem of several variables. Maybe it's not even a calculus problem, but I view it as a calculus problem. You can just strip this part away, because this is really the variable part, and study this function, f of x, a function of n variables, tangent 1/2 xk, where xk is sum to pi, so they're in some sort of simplex, and they're also restricted to all belonging to the interval 0 to pi3. It's a reasonable exercise. I mean, I'm guessing the typical undergraduate math major, with an evening, maybe in the class where you're doing Lagrange multipliers and stuff would sit down and do it. This is one way. This is one approach. Another approach is just to write the area in terms of the support function and work on it. Okay, so a corollary to what we've been discussing, or its own individual theorem, could be stated as follows. So I'm not going to give the details, but the statement is here. So if I look at this area, so if I look at this integral, I can just consider it a function of h, where h satisfies these two constraints. One, the basic constant width constraint, and then this convexity constraint, if you will. Then it's possible to argue directly. So it's actually easy to argue about the upper bound. Once I have this condition, then the average of h is equal to 1/2, and then you can use something called Werdinger's inequality. It's a classical inequality. It's equivalent to the isoperimetric inequality, which isn't surprising because we use Broom-Minkowski. So the upper bound usually can find a multitude of ways. The lower bound is tricky. One of my old professors, I was an undergraduate at Georgia Tech, and one of my old professors, Evans Harold, had written a paper, or has written a paper some years ago, where he analyzed this and studied the variational problem. It's not a typical variational problem. And he studied it and showed that the lower bound has to be this, which is the area of the Rouleaux Triangle. And one upside of what he did, the classical proofs using geometry, you don't get uniqueness out of them, but in his argument, using an ODE analysis, he was able to deduce uniqueness up to rigid motions. So I say ODE analysis. So there's no one equation that characterizes the minimizers, but on pieces of the curve, he was able to analyze some ODE should hold, and was able to match things up to figure out that a minimizer has to be the Rouleaux triangle. Okay, so let's see, it's 5:11. I think I'm doing okay on time. This is a good time actually to stop for questions too, because I'm going to talk now about the problem in 3 dimensions. But were there any questions or remarks?
There wasn't any questions in chat, but maybe someone wants to ask out loud.
All right, well, I will continue, and at any moment there's an opportunity to ask a question. Okay, so now we're all familiar with what is known. Well, I should say many more things are known about curves of constant width. I've been interested, just probably motivated by the conjecture I'll tell you about, but by this area or volume problem. But I do think it's represented. I mean, I'm focusing mostly on the area or volume problem, but I think it's interesting because it's a non-standard problem, and there are a few other problems in convex geometry, and even another conjecture known as Meissner's conjecture. There's also, I mean, there are a variety of problems which I think have a similar, has some similar features to this one, but this is the one that I just happen to know more about. Okay, all right, well, back on topic here. So what about 3-dimensional shapes of constant width? So they're defined similarly. We can define constant width in any dimension. In fact, how would I define it in 3 dimensions? Well, for any 2 parallel supporting planes now instead of lines, the distance is 1 between them for any direction. Okay, so here's a shape which is a true blue set of constant width in R3. Yeah, I played around. You can do a similar parameterization. We essentially use a polar coordinates in 2D, so you need to make some choice: spherical, polar, or or some different coordinates, isothermal coordinates, or given a parameterization of the sphere, you can give a parameterization of bodies of constant width based on those coordinates. So I chose one, maybe spherical, polar, and played around until I got something to work. So here's an example, and like I said, so they're defined similarly. Equivalently, you could require that the projection onto any line, which it will be an interval, has length 1. So that's another way to specify constant width shapes. Okay, so again, this is just some example that I cooked up. The most simplest example is a ball of radius 1/2. For the reasons we discussed earlier, if I look at any two supporting planes, well, they're both going to be distance 1/2 from the center of the ball, and so that does it for you. We can take certain shapes in 2 dimensions, ones which have symmetry about, one which have some reflectional symmetry, like the Rouleaux Triangle, and we can rotate that around its line of symmetry, which turns into an axis of symmetry, and get a shape, and check that it indeed is a shape of constant width. It's not too hard to do it. So there are a couple of examples, and there are more. I could take the pentagon, and any regular Rouleaux polygon will have an axis of symmetry, and so you can cook up a variety of examples. Okay, but again, we're or at least I've been interested in this volume maximization and minimization problem. The maximization problem turns out to be easy. The easy to solve in the sense of it doesn't use anything more sophisticated than what we discussed before. The argument actually works in any dimension, but I'll stick with 3. We can show, not too difficult, that any body of constant width satisfies this equation. K plus its negative is the ball. I'm writing B now instead of D. The unit ball in R3, and that's actually if and only if. And using that equation with the corresponding Blumenkowski inequality in R3, which states that the 1/3 power of the volume is concave or superlinear, then just retracing our steps for what we did with the area, we may conclude that the volume of K is bounded by the volume of the ball of radius 1/2, and uniquely so, in fact. And so the ball maximizes volume among all shapes, the ball of radius 1/2 among all shapes of width 1. And like I said, in any dimension you can do it, do this same argument. And it actually is not such a big surprise because, again, the volume is concave, strictly concave, in fact. And so it wouldn't surprise you that there's a unique maximizer, it just happens to be the ball. All right, well, an immediate question is, well, now after what we've seen is, well, what's true about the minimizing bodies? Well, it's known that there is at least one volume minimizing body. The theorem is usually considered the reason is usually attributed to something called the Blaschke selection theorem, which asserts that if I have a sequence of convex bodies all in a common bounded domain, then they will have a this sequence will have a subsequence that converges in a strong enough topology to ensure that well, actually, sorry, I'm getting ahead of myself. The selection principle itself is just a compactness. Says that if I have sequence of convex bodies all in a common, say all in a common ball in R3, then there'll be a subsequence that converges in the Hausdorff topology. And using that and the fact that the area is lower semi-continuous and in the right way, then you can verify that indeed there is a minimizing body. Using the support function, I don't see this argument so much in the literature, but this can actually be seen as a relatively easy consequence of familiar things like our Rouleaux theorem, which you can just use on the support function. So that turns out also, I use the term easy. I mean, some of you may know a lot more about these types of methods than I do, but they're pretty standard tool, and it's been known for a long time. So not trivial, and I don't want to minimize the contributions of Blaschke and past geometers, but considered a relatively standard method nowadays. An unsolved problem is to find the volume minimizing bodies. Okay, so, or I mean, it'd be interesting just to even give some specific information on them. And I write bodies here because we don't know that there is a unique volume minimizing body. There may be more than one. We just know that there's at least one. Now, based on our experience with the Rouleaux triangle, well, we can try to do, do a similar construction. Okay, and so one way to go is to take a regular tetrahedron. So this is a simplex in R3, where it's four-sided, and each of the four sides is an equilateral triangle with side length 1. So it has 4 vertices. I can take a ball of radius 1, centered around each vertex, look at the intersection, and that gives me a shape which is here on the right. Some people might call that a Rulo Tetrahedron. All right, and then now you can ask, well, how does this do? What's the volume? Does it, how does it compare? Can we compute it? I will say it's actually a non-trivial thing, even to compute the volume in the surface area of this shape on the right. I mean, over the break when I was thinking about this, I confess, yeah, it wasn't so obvious. And I looked up online to see what was known, and some guy had written a web page where he wanted just to get it down because he, just get the calculation, put it out there, because he spent some time on it. He was working in some other area, number theory or something, and he wanted to publish it, but ran into some issues, but thought, the world should know. So yeah, it's maybe worthy of a little bit of thought. Unfortunately, the Rouleaux tetrahedron does not have constant width. And so I write here the minimal width is bigger than 1. One thing that I didn't say is a body of constant width has diameter 1. In fact, if you take any 2 supporting planes, they will be joined by a segment contained entirely with, or the 2 points at which supporting lines touch your body of constant width are distance 1 apart, it turns out. And so this Rouleaux tetrahedron has points, pairs of points that have distance bigger than 1, but not by much. And how you can see it, well, if you really wanted to calculate, if I took, so there's 6 edges, 3 that you can see and kind of 3 on the horizon. If I take the midpoint, let's see, how am I doing on time? Okay, 5:22. So if I take the midpoint of this arc and the midpoint of kind of the opposite arc, you can compute the distance, and it's something like, well, if you do it numerically, it's something like 1.025. And so it fails to have diameter 1 and in particular width 1. So that's a little disappointing, but it turns out that you can alter the Rouleaux tetrahedron and perform surgery to generate 2 surfaces which have constant width. And this is one of Meissner's contributions. His main contribution to this subject, but apparently he did quite a bit of science in his career. He was a professor at what's now ETH. I forget what it was called, Swiss Federal something before. So he was a student there and studied in Göttingen under Hilbert, under Klein, under various people, and went back to what's now ETH and was a professor there for some years. my introduction to this topic is this book, Convex Figures. It's a fantastic book, has all this stuff about 2D shapes, non-trivial theorems, just really great work. I think it's a book that might go back to the 50s. It's by Yaglom and Boltiansky, who were Soviet mathematicians. So it's translated. The translation is great. I learned quite a bit from it. And so there are a bunch of shapes of the bodies I'm going to show you that are on the internet, but I think these are the best pictures because they show exactly how the surgery procedure takes place. So without further ado, here are the shapes. So let's just go in chronological order here. So this is the Rouleaux Tetrahedron. And so inscribed in it is the regular tetrahedron, the one that we discussed. And what Rouleaux did was he identified 3 edges. Okay, so first on this shape B, so these are 3 edges with a common vertex, just the topmost vertex right here. And then what he did was he looked at the plane, which is parallel to this side, kind of the leftmost side shown to you of the tetrahedron, and then say the face that's more broadest to you. And so when you look at those planes, they intersect this body in a few places, namely in this circular arc right here, and in this circular arc. And so these, you know, say this plane, which is, so it's not drawn for you here, but I'm just asking you to imagine it, which is on the leftmost side of the tetrahedron. So it goes through the center of the sphere of which you see, you know, the portion of the sphere you see that's most broadest to you. And so in particular, that intersection is a circle. It is a portion of a circle, I should say. It is an arc of a circle. And so I have 2 arcs of circles of the same radius 1. And what I can do then is chop this piece out and replace it by a portion of the corresponding surface of revolution. That's known as a spindle twist. Okay, so if I take one of these circular arcs and just rotate it 360 degrees, and I get this figure right here. That's a spindle torus. But I just want to do it for a portion, just in this angle between these 2 planes, this dihedral angle. And when I get this shape, I can just slide it right in there, and the shape of the body is continuous. It's a nice continuous shape. It's actually, yeah, it just fits very nicely in there, and I can do that for all 3 of these vertices. So you see I have these wedges, and so I cut those pieces out, insert the appropriate spindle, and then I get this shape down here, which is called A. And it turns out this guy is a shape of constant width. And likewise, instead of the first construction, I could look at 3 edges, which you know, it's a good way to say it, form, you know, something like a Rouleaux triangle. And I can do a similar construction, and then I get another shape. And this gives me 2 shapes of constant width. And it's a great, I mean, just on its own, even forgetting about the minimum problem, it's just amazing to have that sort of geometrical insight from years and years ago. These shapes, I should say, are in many museums all across the world. One's in Harvard. One might be in, I'm trying to think, I've been to Göttingen. I'm not sure if one was there, but yeah, they're, I mean, in many places, it was really just kind of a geometrical feat. And both of these shapes turns out to have the same volume, which is stated right here. So it's about 0.42. It is non-trivial to compute this. I don't know of any easy calculation to do it. This cosine of 1/3 was that dihedral angle, the angle between 2 of those planes that we were just discussing. So it's natural that it shows up. And this is the least known volume for a body of constant width. And there have been at least 2 serious numerical studies that I know of, maybe more that are out there, that in some sense verify this. One did a volume minimization and came up with a shape pretty close to the Meissner, one of the Meissner bodies. And one, there's a method for randomly generating shapes, or generating a shape from a two-dimensional shape of constant width, and then those authors randomly generated many of them, hundreds of thousands of them, and computed the volume and didn't get anything smaller. So there is evidence that this is the shape of Leaf's body. I think most people working in this area believe that. And this is the conjecture due to Meissner, that these bodies have least volume among all constant width bodies. It is unknown if Meissner stated this conjecture himself. It was known to Bonesson and Fenchel, who were in the next generation of convex geometers, and people like Courant in his book on geometry and imagination. So it's been around for a while. I don't know the origin of it. It typically goes by Meissner's conjecture. I want to ask Arena, is it okay if I go over like 2 minutes? I have a couple of basic questions that I want to ask. This is really all the math, but there are a couple of basic questions. Maybe 3 minutes. Is that okay?
Okay. Okay, sure.
Okay, so I have 3 questions. So 1 minute a question. Okay, so going back to our previous experience, we can talk about extreme sets. So K is extreme if it is a non-trivial combination of constant width bodies. Okay, the question is, which bodies of constant width in R3 are extreme? I don't know the answer. Maybe it's known somewhere in the literature. I didn't see it. I do not know the answer, and I don't know of any analog of Calais theorem. Bruminkowski would imply that volume minimizers must be extreme. So it'd be nice to know what are the extreme shapes. In particular, are the Meissner bodies extreme? That's a question. And that could be buried in the literature somewhere. I happen not to know the answer. Okay, another question involves the in radius and circumradius. So it turns out for constant width shapes, the in radius, the largest, the radius of the largest ball contained in the shape, and the circumradius, the smallest radius of balls that contain the shape, sum to 1. And in fact, the in ball and the circum ball are concentric, in fact. So I'm showing it to you here in 2 dimensions, but these are general facts known for all dimensions. And so this is just, again, shown to you in 2 dimensions. So it is known that in 2D, the Rouleaux Triangle, say, has the largest circumradius or the smallest inner radius. The only thing we know about the Meissner bodies, in my mind, that's kind of distinguishing, is that they also have the largest circumradius or the smallest inner radius. And in fact, any body of constant width that includes, just by set inclusion, the regular simplex will have this property. And the Meissner body is one such, 2 such bodies, say, in R3. And then the question I have is there some sort of relationship? I mean, so obviously V of K, the volume, is going to be bounded by 4 pi over 3 times RK cubed, because K is a subset of the circumball. But I wonder if I vary R, so if you give me 2 bodies, one has smaller circumradius, does the volumes go the other way? Is there maybe some inverse relationship, just specific to bodies of constant width? That might be wishful, I know, but it's a question. Okay, and then the last question is, well, I can talk about my support function as before, except now I'm going to pick directions in S2, the unit ball. So this is just schematic picture. And for a given direction, well, I can, I look at the distance to the corresponding supporting plane, and that gives me h of u, and that gives me a function defined now in the sphere. Well, what I can do is I can identify what it means to be constant width and what the convexity constraint is. So this is our analog of h double prime theta plus h of theta. This is now Hessian and spherical coordinates. I can write down the volume. It is a non-trivial calculation to write the volume this way. The volume is usually given in terms of some determinants or a determinant expression, and but integrating by parts and massaging things. So I shouldn't say it's non-trivial. It just takes a little bit of work. You can massage the volume down to this. And then I'd like to know, well, what necessary conditions can you extract from minimizers? The only one that I know that's really worth quoting is due to Uday and Lanchard Robert about a dozen years ago. And they proved that any minimizer has the property that if, at one point, if it's smooth, that if I go to, if I look at the supporting hyperplane at that point, and then go now to the other side of the figure with a parallel supporting plane, then wherever it touches can't be smooth. And so that's the best we know. And I thank you for your attention, and I will stop here.
Thank you very much. I'll clap, and other people clap virtually. I did not see any questions in the chat, so maybe someone just unmute yourself and ask what questions do you have?
Sure. Oh, I see Radmila. Oh yeah, hi Radmila.
Hi.
Yeah, great to see you. Is Andrew there, or is Andrew in Philly? I guess he's there probably, right? Okay, I can't hear anything, Radmila, but anyway.
So any questions?
Yeah.
To the speaker?
Well, I was just curious about, you had a question at the beginning with the inner and outer ready. Your first question, I think.
Yeah.
Can you show it again, or?
Sure. Let me share the screen again. Okay, whoops. Let's see. Yes, 3 questions. Yes. Okay, why am I not going there? I don't know why I wanted to go up. There we are. Okay. Yes, there were 2 slides. I mean, here was the second one. Is this what you were looking for?
No, I think that the first one, there was a.
Yes.
Okay, yeah, right. So I see. Okay. Yeah, because I remember the time when he was still alive, talking to Lachlan Robert. There also.
Oh, I didn't know he's not alive anymore. I didn't know that.
No, I mean, he died in 2003. He had a freak accident. He came back from a trip and he was putting back his suitcase. He climbed on a ladder and he fell and he killed himself.
Oh, I only knew Uday. I met Uday at MSRI. I didn't know the co-author.
Yeah, no, Uday is still alive, but Lachlan Robert died, unfortunately. Yeah. So, because I remember the other things, but you have bounds, right? On the, I think you can relate at least in 2D. I'm not sure if there's a 3D.
No, in every D, there's Young's theorem. There's Young's theorem. So Young's theorem tells you how to estimate the circumradius of n points, the smallest points of n points of diameter 1 in Euclidean space, and the diameter is less than or equal to square root of the fraction n over, I think, 2n plus 2. So you do know some estimates on these.
Right. But also, you have relationship between the area and the product of these of the diameter and the in radius, right? I think you have up to a constant, probably 2 here. And then I remember there are conditions for which this equality is actually exact. So if you have a convex body, I think the area is bounded by the product of the 2 times 2, I think, right? And that's true for any convex body. So now if you have a Rouleaux shape, I'm not sure it's one of the bodies that would actually saturate the equations, but I know that there was work in that direction. If you.
No, I don't. This is actually new to me, and yeah, I want to look into this. Yeah, I see where you're going with it. Well, yeah, it'd be curious because since I could write little r in terms of capital R, then that it would be interesting to investigate. Like, is there any information? Is there any information there? Yeah, that's a great comment. But no, I have not looked at it. Yeah. So I mean, the thing that I'm curious about myself is, I think that there's some way to deform these shapes that will decrease volume and increase, say, circumradius. And my question is, can you really tease out some information from this? So that's kind of where the approach that I've been looking at. And it's really, I didn't talk about that today because it's really just at the early stages. But that any constraints would be useful. And I did ask about a relationship. So thank you. That's a great comment.
More questions or comments?
Thank you, Ryan, for this great talk. So you mentioned that it's known that there has to exist this minimizing body, I mean volume-wise, yes. But that proof doesn't give any idea what the volume should be. Is that correct?
That's right. Right. The proof is solely existential, and we can write down. Well, in terms of the support function, you can write down a condition, almost like a derivative zero condition, a variational condition, but it is weak. I mean, as Patrick just was discussing, Blaschke, Robert, and Uday in their work, and they teased out some information, but we don't really have anything strong, I would say, on what it means to be a minimizer, other than those words.
Okay, thank you.
Yeah, no problem.
Any more questions? So could I ask you like a quick question? And sure. So in the planar case, as far as I understood, minimizer is unique, right?
It turns out to be.
And right. So what is substantially, if you could, maybe it's complicated to answer, but what is substantially more difficult in space case versus planar case? Like what of the tools which used in plane case cannot be used in space?
Well, one perhaps an easy answer is, so all right, let's say I want to take, okay, so there are two things I would say. One is so I sketched out one proof in terms of the density of Rouleaux polygons. There is a density result in higher dimension. It's just complicated. The shapes are complicated. They're not as simple. So it's hard to get your hands on and compare shapes. So so in 2D, all the shapes are basically Rouleaux polygons. And I showed you like a formula that you can manipulate. So and that formula, I mean, computing that area, the area of a Rouleaux polygon kind of in general, you can take the finite intersection of balls in R3, and it's known that there'll be some surgery. Actually, given any set of diameter less than or equal to 1, then there's going to be some body of constant width that includes it. And so you might get there by surgery, or however you get there. And so it's just hard to manipulate these sets. So that's one thing. So that's one kind of jump in difficulty. And then if you look at the problem through the support function, so why don't I even just share my slide again, because it may make it a little bit easy to see. So let's see here. So okay, so here's a problem you can study. Just minimize this expression subject to these two constraints. Okay, so for all functions which satisfies these two constraints, and it's a convex problem. So finding the maximizer is a convex problem, and it turns out to be easy. But the minimizer, yeah, it turns out to be tricky. But what you can do, what Evans Harrold did, he derived a necessary condition on various intervals. So as I mentioned, H oscillates between, so it goes above a half and minus a half. So really probably what I ought to do, I actually like to leave it like this, but other people, like some of these other authors I've mentioned, actually all the other authors I've mentioned, usually like to subtract 1/2 from H, because then you get an expression involving just odd functions. And then, so Evans Harrell, this former professor of mine, I think he's professor emeritus now, Georgia Tech, what he did was he was able to derive a condition when H is positive and when H is negative. And because it's continuous, you're going to have intervals for which is positive and which is negative. And he was able to get a differential equation to hold on each of those intervals. And then he was able to solve these equations on each of these intervals and kind of patch them up in a reasonable way. And, you know, if I go to the corresponding problem in 3 dimensions on the sphere, on the 2 sphere, that just seems a lot more difficult. I mean, maybe there's some way to do it. It'd be great to actually understand how to do that better, but it has not happened yet.
Thank you very much. I think we maybe should finish sort of official colloquium, and I will stop recording, and maybe we'll have someone wants to stay around for informal conversations with Ryan.
Sure.
Thank you again.
Oh, my pleasure.